This is a Regents chemistry review of all the math problems that you could see on your June 2015 test. Now, I have listed all of the math problems that have been published in the last 6 printings of the test. So I've gone from June 2012 through January 2015, the last test. And I basically have made a spreadsheet of all of the math problems and the types that I have seen when I went through the test. And what I did was I saw some patterns. And the patterns that I see are that there are some recurring problems that occur almost every year. And I think it'd be a great way to analyze these 6 tests, looking at the types of math problems they have, and be able to identify these types of problems could be very beneficial to your review, since these problems seem to occur almost year to year or every year. For instance, if you look very carefully, the titration problem appears in 5 of the last 6 tests. Only one it was not on was a January 2013. Okay, so if you can see that the titration problem, I would predict is something you would see for the June 2000 test. So my friends in chemistry, let's look at the titration problem and the 5 that have been published in the last 6 tests and see if we can come up with a way to identify them. Okay, so starting with the titration problem in the oldest test of the 6 that I'm looking at or analyzing, I see June 2012. And this is a part 2 question. And you notice it's part 2 because you see that there's a blurb in front and you see that there's some questions that go with that little blurb. All right, this is probably part B2 if I'm not mistaken. But in any case, the question we're after is number 65. Determine the concentration of KOH. Now, you understand there are 3 different concentration terms that you've learned this year. You've learned molarity as a concentration, percent by mass, and part per million. These are all concentration terms that are listed in Table T. So here is Table T in all of its glory. And as we scroll down, we can see that there's some concentration terms that do pop up. And the ones that we're looking at is percent composition, okay, is right here. Part over total times 100, part per million, and the molarity formula. So when you hear concentration, sometimes you think molarity, okay, which by the way is big M. It's written as big M in the word molar. But we also have another place where there's molarity, and that is in the titration formula, where you see big M in all of its glory here as well. Molarity times volume equals molarity times volume. So it gets kind of confusing what we're doing here. So we're going to identify titration problems because we have what we call 3 variables. There's 1, 2, 3 variables that you are going to be given to solve for the 4th. So what I always say, if it's a 3 variable question with molarity, and you can understand it's a titration, you have this formula. So how can I discern if this is a titration problem or molarity? Well, first of all, they use the word titration. Okay, so clearly it's a titration. But if you're not sure, another way to look at this is see that there's 1, there's 2, and there's 3 variables that make sense for our formula, which is nothing more than molarity of the acid times the molarity, times the volume of the acid equals the molarity of the base equals the what? Volume of the base, given to you in Table T. So that's what I'm doing to solve for the concentration, and concentration is the molarity. So I'm solving for the unknown concentration of the base because I know 3 of them. All right, so all you're doing is plugging in. Now, the keys to identify whether you have a titration problem, yes, the word titration is sometimes written. Another key word, okay, is neutralize. Because in a titration, what you're doing is you're figuring how much, in this case, base, which do I have to add to completely neutralize some amount of acid. So if I have some amount of acid, let's say it's the Arrhenius definition with 3 protons, how much of the base do I need to what? Match up every OH minus with a proton to make water. Okay, this would all make 3 water molecules. So we're trying to neutralize how much of each. So you're going to be dealing with an acid, H in front, a base is a hydroxide with a metal. So acids and bases, the word neutralization, titration, 3 variables, all of these scream the titration formula. So let's solve for this very simply. So what did they give me? They gave me 20 milliliters of the acid. Acid has the H in front, table K. It's listed. So I have 0.15 molar. Okay, you plug it in. What else do I have? 20 milliliters. Okay, and then I said, okay, I have 18 milliliters of my volume. How much of my base? And this could be your X if you're comfortable writing the X. So if I am going to solve for this, all I'm doing is now just dividing by 18 if I'm just doing my algebra. 0.15 times 2, or 20 I should say, all right, divided by 18 equals my molarity of B, which is what we're looking for because concentration is that. Now, of course, if you want to use that equal to X, be my host, no big deal. 15 times 20, divide by 18, gives me 0.16666. I'm going to round off to 2 sig figs, least number, just a good habit even though they're not looking for it, and 0.17 molar. You can see that's a pretty simple problem. You're just plugging into your formula. What's difficult is being able to recognize it was a titration formula. Let's go see some others from the last 6 tests. All right, so that was June 2012. Let's go to June 2013. And by the way, if you want to do these with me, on the bottom of the video, I have a link that you can download and print these and stop the video and work with me. So here's another titration problem. How do I know? Well, I see big M, I see which represents molarity, okay? And from that big M, all right, I've got what? 1 variable, 2 variables, 3 variables, okay? And there's the word what? Neutralize. I have acids and bases involved. This is screaming titration. So I plug in. So molarity of my acid, volume of my acid equals molarity of my base, volume of my base. Notice they're solving in molarity. It's a simple plug-in. It's a simple problem once you identify this is a titration problem. Notice this problem did not have the word titration in it. Okay, so let's plug in. Very simple. 10 milliliters of my base, right? Hydroxide, all right, is a base with the salt here with the Na plus. So I've got 10 milliliters. The concentration is what they're looking for, so that's going to be my X. Okay, the molarity of my acid is 0.5, and the volume is 40. Okay, and we can solve for X. Now you're going to 40 times 0.5 is going to be 20. It's half of that. And of course, you're dividing by 10 algebraically. And what you're going to get is X, or the molarity of the base, is equal to 2. All right, and that's what we got here for this answer. Pretty simple, straightforward plug-in, but you have to identify that this is a titration problem. 3 variables, big M, the word neutralize were all the keys for identifying that problem. Here's number January 2014. We're getting closer. Okay, now in this problem, they're mentioning the word titration, which is a technique you use to figure out the concentration, in this case, all right, of the base using a standard solution. So they're telling you, there's a base, there's an acid. How many variables? 1, 2, 3. It's a titration problem. So again, very simple. We use a titration. M of A, V of A equals the molarity of the base, volume of the base. Make sure we put our numbers in correctly. 50 milliliters of the acid. So here's my 50 milliliters. It's my volume, how much I have. Here's my concentration, 0.026. Okay, equals what? Well, what's my molarity? The molarity is 38.5. I'm sorry, they're looking for the molarity, so that's my unknown. The volume is 38.5 milliliters. Put that point in there. Okay, we're solving for X, so it's going to be 0.026 times 50.0, and I'm dividing by this 38.5, and that's just some simple stoichiometry. That equals to X, or the molarity of B. So let's put it into our calculator. and 0.026 times 50 divided by 38.5. Okay, and I get an answer that some people get scared of. It's a decimal place, 0.03, and the least significant number is 3. Actually, 2 sig figs. We'll stay with 2. So 0.034. I'm just rounding off, and that's my molarity. Okay, they didn't ask for sig figs, but I remember the rule. Just in case you do, that's 3 sig figs. That's 2. Why? Leading zeros never count. Ending zeros count if a decimal point is present, and that has 3. So the least significant number in my calculation when I multiply divide is 2. That's all they wanted. And because your calculator says so, you leave it. Do not say, oh, that can't be right because that's an ugly number. No, that's the real number. Okay? So pretty simple to identify our titration problems. Okay? And if you look at the number 2014, June of 2014, we have a laboratory activity, 4 drops of phenolphthalein. I'm betting that most of you did this lab. You'd put phenolphthalein. This turns slight pink when what? When the H pluses approximately equal the OH minuses. It told you to stop adding from the burette. But you don't see that. How many what? We have 1 variable, 2 variables, 3 variables. You see what? Big M. Okay? Any case, moving on. They want you to determine the concentration of HCl, and that should not be a big issue. Same formula. So again, all we're doing is just plugging in. The hardest part is identifying the problem, and all I'm doing is putting the 25 milliliters of the acid under the volume of the acid. They gave me the 0.5 molar of the base that goes here, and the 18.5 milliliters of the base here, and I solve for the molarity of the unknown missing molarity of the acid. Rearrange this according to algebra and solve and get 0.11 molar. Okay, that's 47, and this is in the part 1 or the multiple choice, I should say. Notice, same kind of question. They're telling you what a titration is, and of course they are what? Giving you how many variables? 1, 2, and they're giving you 3. Okay, so you're just plugging it in, and if you want me to do it because you felt like I shouldn't have skipped that one. Okay, so MV of M of the acid, volume of the acid equals the molarity of the base equals the volume of the base. All right, so I've got 20 milliliters of a 0.15 molar of a base. So those go there. 20 milliliters of a base, and I have 0.15 molarity of the base has to equal what? Has to equal 24 milliliters of my acid. It's my volume. What's the concentration? Concentration is the molarity. So we can see that it is 0.125 molar. Very important, okay? Any case, that's how we do it. And again, it's really an easy problem. You just have to be able to identify. Notice they said the word neutralize here. So the second type of problem is the molarity problem. Let's take a look and see how often this problem has appeared, okay, on the Regents in the last 6 published tests. So the molarity problem, okay, has occurred 3 out of the 6 last tests. So either we're not going to see it or we're due for it. So I'm not sure if we're going to see it, but certainly we need to be prepared for it because it is very common. Every other test, 3 out of 6, 50% of the tests have this question. And the reason I want to go over the molarity problem is because it is very similar to a titration problem. And again, I'm all about trying to identify the problems that are most common on this test. So let's go do it. So back at table T, just like the titration formula is given to us, all right, we can see that the molarity formula is given to us right here. It's the moles of solutes, that's the substance being dissolved over the liter of solution. And if you notice, there's how many variables here? There's 1, the molarity itself, sometimes big M is what they use, liter, and moles. So there's 3 variables altogether, but you need 2 to solve for the 3. Whereas in titration, you have 4 variables altogether, which means you need to have 3 of them to solve for the 4th. So titration is a molarity problem where you have 3 variables to solve for the 4th. Molarity problems, although very similar, are different because they're going to give you 2 variables to solve for the 3rd. So let's see if we can discern between those two. So our molarity formula is molarity, big M, sometimes they use the word molar, okay, is equal to the moles of solute over the liter of solution from table T. Notice this is going to have what? Two variables given to solve for the third. Okay, don't forget the opposing problem that's very similar is the titration problem where they have big M also molarity, and you could solve for their concentration this way, but you're going to have three variables, and it's not going to be an acid and base. So let's look at number 59 of the June 2012, our oldest test here. Determine the molarity of the solution. Well, there's two formulas we have for molarity. Which one do we have? Well, very simple. First of all, I count 1, 2, 3 variables. So maybe this is a titration problem. So 1.4 moles. There's no moles in a titration formula. There's liters for volume, and 85 grams per mole, that's not a unit that we're using here. So there's really only two variables that we have. We have the moles of the substance being dissolved, right? And we have the amount of water. And they want the molarity. That's it. This is called a formula mass or gram formula mass, and it's not part of either formula. So all I'm going to do is use my formula, moles over liter. They gave me two variables. 1.4 moles goes over 2.0. And what do I have? I have a 0.7 molar solution. That's all they want you to do there. Notice there was no titration. There was no acids and base. There was no phenolphthalein. There was no word neutralized. This is clearly a molarity problem. I hope you can see that difference because it is on 50% of the test. There's a good chance you'll see it. Let's see another one, January 2013. So we've got something else dissolved. Notice that might be a great way to recognize this because molarity is about solutes being dissolved. So something else is dissolved. I don't see the word titration. Okay. Look what they say. Determine the number of moles. Can I get moles? And I got liters. So if you notice, what are they giving me? They're giving me the concentration and they're giving me the liters. These are two out of the three variables in my molarity formula. Molarity, big M, is moles over liter. There's no word neutralization. There's no three variables. This is clearly not a titration problem. And you know, in a titration problem, I cannot solve for moles. I'm solving for what? Volume or molarity. Molarity is not moles, it's moles per liter. So this is screaming to you that we're dealing with, a molarity problem. So how do I solve for it? Very simple. What are my moles? My moles are, well, they didn't give me my moles. They're actually to solve for the moles itself. So we're going to solve for the moles. Okay, so I have the molarity, which is 0.10 m. I have the liters. There's 2.0 liters. Okay, here are my moles. And algebra, that could be your x if you're comfortable doing that. Solve for your x on top, and what you're going to get is you're going to get moles or x, doesn't matter, equals 0.10 times 2.0. Okay, 2 times 0.1 is 0.2. And we got 0.2 moles as our answer. So I'm solving for the what? The unknown in my molarity formula. I knew it was molarity because it was dissolving something in water, and I had the molarity. I had two variables. There was no titration here, no acid and base, no neutralization. Let's go see another one. Okay, and they're not hard. All right, so this is the last of the group. Okay, and let me move this over a little bit. Okay, so determine the molarity of the solution. Well, what do we have? Something else is dissolved. So the key word for molarity might be the word dissolved. And again, how many variables are they giving me? 1, there's the liter, there's my volume, there's my moles. There's no moles given in a titration problem. So molarity is equal to moles over liter. Okay, so what do I have? I have 1.25 moles over 2.50 liters. And when I do the math, I get 0.5, let's say 0, big M for molar. That's all I'm doing. I'm plugging into my molarity formula. So again, the reason for me giving you the same problems, the same types, is so you can recognize clearly that molarity problems, on top of the fact that there's only two variables, they all said the word what? Dissolved, okay, with two variables. All right? So that might be a key for you. Two variables, big M, molarity. Three variables. Another problem that comes up very often in these tests is a conversion from mole to grams or grams to moles. So as you see, of the last 6 tests, there have been 4 published tests of the last 6 that had some kind of conversion of grams to moles and moles to grams. And it's a very common and very important calculation, so I do predict we'll see it. Not sure what the molarity formula, but darn right you have to be able to make sure you know it. So in any case, let's take a look at these 4 problems and see if we can be able to identify them. Now, we know that mole is connected to molarity, moles over liter. So there is some similarities here, but let's go take a look at them. So in this question number 57, we've seen this question or this blurb before when we were doing molarity questions. So they're now asking for number 57, show a numerical setup, just the setup, don't need the answer, of course a correct setup for calculating the mass of the solute used to make the solution. So now we want mass. Okay, we've been dealing with molarity, which we now know has moles in it. We know that molarity is also in the titration formula, okay, for the 3 variable scenario. But now we're dealing with mass. And the way that we can get mass is that mass can be interconverted into moles. Moles and mass can be interconverted. In fact, if you did the mole diagram in your course, you've got mole in the middle, and you should know that grams can go to moles. Okay, this is mole. M-O-L-E, not molarity, and mole can go to liters, and then mole can actually go to the number it represents, which is Avogadro's number. I always say number of stuff here. Now we know that's called a very famous mole diagram, but for all intents and purposes, this course, it focuses primarily on grams to moles and moles to grams. These other conversions, 1 mole is equal to 22.4 liters, and 1 mole equals Avogadro's number, 6.02 times 10 to the 23 third, is not calculated for. So this is where you're going to see all of your conversions from mole to grams. Now, how do we go from moles to grams and grams to moles? Well, we use the formula mass. So what they gave me here, they gave me 1.5 moles of sodium nitrate, and you want grams. So as I have taught you and other people have taught you, use your units here. Okay, so what I'm going to do is make some room here. I'm going to do is I'm going to use my units. I see that it's a mole that was given, so I'm going to put mole on the bottom. And I want the unit grams on top. For every 1 mole is how many grams? How many grams equals 1 mole? That, my friends, is called a formula mass. To do that, I would take the sodium nitrate, okay, that you probably should know is sodium is +1, nitrate is -1 from table E, and you can figure out the mass of sodium, nitrogen, and oxygen and add it all together using the atomic masses. We call that a gram formula mass. We don't have to do that because they already gave me the number. They told me the what? The formula mass of sodium nitrate is 85 grams per mole. So that is what's going to go right here, 85. So all they want for the setup is 1.5 times 85. That's it. That's all you needed. And that's how you convert from the mass to the moles. Okay? So yeah, it looks like it's another type of problem, but they just want the mass. And you're calculating the mass, okay? If you've got moles, you know you can do that. Mass to moles. Or grams to moles, moles to grams is a converting factor. Let's take a couple look at other ones. Easy for me to see, or say, I should say. So January 2013, what does this look like? Well, I've got a sample of a green vegetable. Well, thank you for telling me it's green. But let's look at it. So I've got 0.003 grams of boron. Okay, don't be a boron. How many moles do we have? Well, we got grams, we can go to moles. Moles, we can go to grams. So they're giving me 0.0035 grams. And I want to go to moles in this case. Notice I was given grams. So I'm going to get rid of the unit that I have started with and put that on the bottom to get the unit I want, 1 mole. So 1 mole is how many grams? Well, now they didn't give me formula mass or molecular mass of boron. I have to know that I need it. So notice I'm putting grams on the bottom here, unlike the question above, because I am trying to get rid of grams. In the other question, we were given moles to go to grams. So this is the opposite. Mass or grams can go to moles. Moles can go to grams. But I need a what? I need a converting factor. Okay, I need a number that goes from grams to moles, and that's what we use from the periodic table. So we need to go to the periodic table and find boron. Let's do that. So let's be a boron here, and see the atomic mass of boron is 10.81. What does that tell me? It tells me that the most common isotope is 11, but it also tells me that 11 grams, I'm just rounding that off to a whole number, equals 1 mole. Okay, so that's my converting factor. So I put the 11 here. Now they want you to determine the total number of moles, so we have to calculate here. So I take my handy dandy calculator. Okay, take 0.0035 times 1 divide by 11, and I got a small number, and people get afraid of these numbers and don't. Okay, the answer is 0.0003 2. Okay, so 1, 2, 3, 4. And my calculator actually said 3.2 times 10 to the negative 4. That you could have put down as well if you're dealing with a scientific calculator. But that's your answer. And don't say, well, that can't be right. It doesn't look right. No, it's small. Okay, and it's okay. That's the answer. And of course, that's in moles. No big deal. Very simple. The hardest part is identifying the problem. Grams to moles, moles to grams. Let's go to June 2014. Another blurb, but they want you to determine the what? The total number of moles of CO2 to the tank. Now, for part 2, I always tell my students, go to the questions first before you read the blurb, because the blurb has a lot of information that might turn you off or intimidate students. Maybe you're not one of those, but if you read this and say, oh my gosh, 508 cubic centimeters, you're like, oh, okay, what's going on here? But all they want, okay, and this is very important, there is always an easy solution to all of these problems. You're just going to have to be able to what? Identify them. That's why I'm here. So determine the total number of moles of CO2 added. All right, well, to get moles, what can I use here? Well, there it is. I mean, there's the grams. Grams to moles, moles to grams. Just be aware. So I have 340 grams. I want to get rid of grams to get what? Moles. I'm using my units to help me remember if I'm multiplying or dividing. I know some teachers don't teach using the units. They actually have them memorize when to multiply or divide, and I just don't really like that too much. So here's my grams. I want to get rid of grams, so grams goes in the bottom. And 1 mole is how many grams of what? Of CO2. Well, they didn't give me a formula mass or molecular mass, so I'm going to have to go to the periodic table. And now I'm going to have to do something called a molecular mass, aka formula mass. I'm going to have to find the grams per 1 mole using the formula. So in 1 mole of these, I have 1 carbon atom. 1 times the atomic mass of carbon is 12. And I got that from the periodic table. There's the mass. And 1 times 12 is, I think, 12. Then in 1 mole of CO2, I have 2 moles of oxygen atoms. 2 times the mass of oxygen, which is 16. I'll show you where I got that. I got that from the atomic mass of oxygen on the periodic table. That gives me 32. And that's a total of what? 44 grams per mole. I just did a molecular mass, but more importantly, I understand that this number is my converting factor from grams to mole. So I put that right here. That's my 44. Okay, sometimes they give it to you, sometimes you have to calculate it. This could be a problem all in itself. We'll talk about that. So take a calculator out, and all you're doing very simply is taking 340. Okay, using your units, you know you're dividing by 44 because you have to get rid of those grams to get to moles. That's why it's nice to use the units. There's no memorization of when to multiply or divide. Any case, I get 7.7. Okay, 7.73 or 7.7 is good. They didn't ask for significant figures, so this gives me approximately 7.7 moles. Pretty straightforward questions, guys. You just, again, have to be able to what? Identify it. Okay, I think our last one I'll do is we've got a blurb here, and they want the moles of copper. Okay, again, there's no solution, there's no molarity here, but there is the grams of copper. So given the grams of copper, I write down the unit, 30.1 grams. And certainly, guys, you can always pause me to do the problem yourself. Of course, we do number 70, and then, you know, see how I do it. No need to me to do it all for you. But in any case, I'm getting right down to it. Going to get rid of the grams. The grams go on the bottom. I use my units to remember how to actually, well, to figure out if I'm multiplying or dividing here. So 1 mole, because I'm solving for mole, goes on top. The unit I was given is on the bottom to cancel. I need some number here. Now, what am I using? Well, the copper. So we've got to go somewhere. Okay, now it's just copper. If it was bonded to something else, we'd have to do what we did for CO2 and do a molecular or formula mass, but we go to the periodic table. And I want to take the atomic mass of copper, 63.546, and round that to 64. 64, there she goes. Grams cancel, and all I'm doing is 30.1 divided by 64. And I get 0.47. And I guess it should stay with 3 sig figs. I started with 3, so 0.470 is the proper way. 0.470, and I'm left standing as moles. Pretty straightforward. Grams to moles, moles to grams. They're asking for moles. If they get the grams, hey, do that conversion. Okay? Now, of course, don't fall in love with the fact that you have to be moles to grams, grams to moles. As I've shown you, you can also figure out moles through molarity, right? Okay? So if you look at a question we just did, all right, and I think they're asking for moles up here, number 62. No. Yeah. Determine the moles. So here they're determining the moles. Okay, but now, of course, it's producing 2 liters and something was dissolved. So you can see if you're solving for moles, it doesn't have to be grams. You could use the molarity formula. So don't fall in love with just the idea that it can only be this way. But look at the indicators that it would be a molarity problem. Dissolved, big M, 2 variables, so forth and so on. Hopefully, this is getting clear to you now. Now, another related problem. You noticed in order for us to convert from moles to grams and grams to moles in the 4 questions we just saw, that we needed the formula or molecular mass. Using the periodic table and using the mass per 1 mole of each atom, its atomic mass, we were able to solve for or use that number as a converting factor to do this conversion. But sometimes, as I said before, finding that number, the mass per 1 mole, by using the individual atoms' atomic masses from the periodic table is a question in of itself. So you can see that out of the last 6 tests, there have been 4 questions that just asked for you to solve for the formula mass. So you should be able to identify it. So let's do that. So I'm on top, page 16, I believe. Let's go find that, make sure. So I'm sorry, top of 17. That's where I am right now. If you have this packet with you or you download it, all you have to do is look at the bottom of the video here, and I do have a link where I'm talking about, I have a link below. Any case, moving forward, they just want you to find the gram formula mass of this. They want the mass of the entire formula. Now, what gets confusing sometimes is people don't know how many of these things. This 3 means you have 3 ammoniums, 3 NH4s. Okay, so 3 NH4s. And it makes sense why you would need 3. From table E, each one of these are called an ammonium ion or +1. So this is the whole thing is +3. A phosphate ion, by the way, is -3. So it makes sense you would need 3 of these positives with one of this -3 to make a neutral compound. Okay, this is an ionic compound. Pretty cool it's an ionic compound that has no metals in it because it's a positive attracting a negative right there. Okay, now what they're after is just how much grams per mole. So as we said before, all we're doing is adding up the masses of each of the atoms, but you have to get the right number of atoms. So this 3 means you have 3 of everything inside, so there's 3 N's. So in 1 mole of this compound, there are 3 moles of N atoms. So 3 times the mass of N, which by the way is atomic mass of 14. Rounding it to 14, there it is. And 3 times 14 is 42. All right. And then of course we have 3 times the individual number of H's. So there's 4 in one of these. Since we have 3 of them, 3 times 4 is 12 hydrogens. And that makes sense. If you got 3 of these, okay, and you count all the H's, you'd get 12. So 4 times 3. So my friends in chemistry, make sure you do not add these numbers. Careless mistakes, and people think there's 7 H's. No, there's 4 times 3, there's 12. So 12 times the atomic mass of each hydrogen, which is 1, rounding to 1 from the atomic mass. So 12 times 1, I think, is 12. All right, and then we have, okay, 1 phosphorus. So one of these times its atomic mass, which you can believe me now is 31. Okay, I don't think we have to go there anymore. And then we have 4 oxygens. All right. In 1 mole of this, there's 4 moles of oxygen atoms, so 4 times the atomic mass of 16. Okay, so 4 times 16, what do we got here? 32, 64. And then we have 1 times 31, of course, is 31. We add these together using our calculator, or if you'd like to venture out and do it by hand, you can. Plus 12, so 42 plus 12 plus 31 plus 64, and you get 149. Okay, very, very simple question, but there are some people who get it wrong. Be able to identify that. Okay, moving forward, and they don't get any tougher than that, but sometimes they throw a little wrinkle. Like number 59, number 60, a part 2 question. They want the gram formula mass. Okay, and then sometimes they say, well, what's formula mass and what's gram formula mass? It's the same thing. Okay, the mass of butene. Only way to get a mass of a compound is to add up all the individual atomic masses anyway. Well, 1 butene, E means a double bond, it's on the first carbon, so we're dealing with this compound. So first of all, I need to have a chemical formula. Well, there's 1, 2, 3, 4 carbons, C4. And there's 1, 2, 3, 4, 5, 6, 7, 8 H's. But you probably already knew if it was unsaturated and it was an alkene, the general formula given to you in table Q is CnH2n. That means double the amount of H's compared to the carbon. All right, well, what do they want? They want a gram formula mass. Gram formula mass, another way of saying formula mass, the mass per 1 mole. So you got 4 carbons. All right, in 1 mole of that compound, C4H8, you have 4 moles of carbon atoms. 4 times the mass of a carbon atom, which if we go to periodic table, its mass is 12. That'd be 48. You can just trust me on this one. And then, of course, you have 8 hydrogens. 8 times the mass of a single hydrogen atom, because we said that in one of these there's 8 moles of hydrogen atoms, and a mole of hydrogen atoms is its atomic mass, which you rounded off to 1. And all you get when you add these together, you get 56 grams per mole. Pretty straightforward. Now a little tiny wrinkle because maybe you didn't know which one to add up, although they did tell you the one with 2 bromides is 1,2-dibromobutane. No big deal. Next one, kind of very similar one here. I determine the molar mass of the product. Now this, oh my gosh, molar mass, what is that? Okay, it's another way of saying, now you could say the word molecular mass, probably I prefer that, but molar mass is the mass per 1 mole, but molecular mass is what these compounds are. They want the product. These are all covalent bonds, so they're usually not going to use the word formula mass, but they could. Molecular mass, formula mass, gram formula mass, it's always the same thing. Mass of the entire formula. I'm not sure why I do that. Formula mass. Yeah, I did that today. Okay. Molar mass, the mass per 1 mole. It's all the same thing. So C2H6, this is a saturated hydrocarbon, totaling the maximum number of H's because they're single bonds. The one that I had above that we just did is unsaturated, has under the max amount of H's, right? Because if it didn't have this bond here, every carbon must make 4 bonds. We would have another H here and another H here if that double bond wasn't there. We'd hold more H's. We'd be saturated. But it's unsaturated alkenes, where alkanes are saturated. In any case, very simple problem. I have C2H6. In 1 mole of that, I have 2 moles of carbon atoms. 2 times the atomic mass of carbon is 12, 24. You have 6 moles of hydrogen atoms in 1 mole of that. 6 times 1 gives me 6. Again, for those that are just checking in, I get these numbers directly from the atomic mass of each of these elements. Okay? In any case, I add these together and I get 32 grams. How about 30? Yeah. I ventured out away from the calculator and I failed myself. Okay, so 30 grams per mole. Okay, pretty straightforward. All right. So a formula mass question is just that. Add up the mass of the formula. Okay, and here's another example. Okay, if you want to pause this, you can pause me now and I'll come back and I will show you how it's done. And voila, I've done the problem. I've taken the what? The atomic masses from the periodic table to find the mass of each of these atoms. I multiplied by how many of them were in the compound. Okay, and we found a gram total of 242 grams per mole, choice 4. Pretty straightforward. But again, understand that this number, solving for this mass per 1 mole with a couple of different names, could be a problem in and of itself, but it also can be used to go from what? Moles to grams and grams to moles. It's an important conversion factor. Now there's another way that we use gram formula mass, and gram formula mass or the mass per 1 mole of the compound or atom is also used in problems that are called percent by mass. Let's go see how many percent by mass questions appear on the Regents. So here we are back with that first sheet here where I've separated and kind of collated the type of problems you'll see here. So percent by mass, of the last 6 tests that have been published, okay, we can see that there have been 4% by mass, okay, and there they are. So 4 out of 6 means that that occurs very often, and my guess you'll see it. So let's take a look at some percent by mass problems. So percent by mass problems are based on the formula of certainly part over total times 100. Okay, and you could find it in reference table T. It's under percent composition on the last page, and basically it's the part over total times 100. That's a percent. It's always percent by the mass. So what we're going to do here with this question on June 2012, they wanted the percent by mass, but just a numerical setup for calculating the percent error. So what we need to do is we need to find the total mass. Now let's pick a part, mass of 1 mole. So the total is going to be the what? From the formula mass. The formula mass will be that total. Since it's a percentage, it doesn't matter on what size sample you use, so we pick a mole. And because we do that, we can use the total as the formula mass. So what we're going to have to do is do a formula mass to put that number on the bottom. So let's do that. We have 1K, and what I want to do is stop me now and do it yourself, or just let me just click on and let me continue, and I'll show you how it's done. And there it is. All I did was basically a formula mass of the entire compound. Only thing that may look a little different in you is I kept my water molecules together, and I know that 1 water molecule is made of 2 H's. Each H is 2 times the mass of one hydrogen, which is 1, plus in one water molecule there's 1 mole of oxygen atoms. 1 times 16 is 16, and certainly a mole of oxygen is 18. Since I had 12 of them, I just kept that together. Okay, we did this with hydrate problems. Any case, so the part is a 216 over the what? The total times 100. That's all they wanted there. Okay, but you needed a what? You needed a formula mass to do that. So you can see how formula mass helps us in other problems. January 2013. Okay, we have a part 2 that's kind of strange, a hard candy lollipop recipe that I know all you guys are going to follow after this. Okay, so let's go to 84 at some point, and let me just move this back so we can see what's going on. 84 says determine the concentration expressed as percent by mass of the sugar dissolved in the mixture in step 1. So they want the percent by mass of what part? They're asking for sugar. Make sure you can clearly understand what part they're asking for. So percent by mass of step 1. Well, what's happening in step 1? In step 1, in a saucepan, we mix sugar and water. There's nothing else. So part over total times 100. And there we go. So we only have 2 things in step 1, sugar and water. So the total, now we're not using the formula mass, but we're adding up the total amount. So 414 plus 177. So put that in your handy dandy calculator. Plus 177. I get 591. 591. And the part they're asking for, if you forget, just mosey on down to the bottom. We'll see that they're asking for the sugar, which is 414. That goes on top. And we're timesing by 100. And that's all it is, the part over the total. Different kind of question, but is an easy solution to every answer. Okay, so I get 70% approximately, about 70%. Very simple, not too bad, but you have to be able to recognize it. Okay, next question, percent by mass. Determine the percent by mass of carbon in baking soda. All right, well, if you didn't know what baking soda is, you go back to the reading, and baking soda is that guy right there. Okay, so look what they gave us. We know it's part over total times 100. My friends in chemistry, what's the total? Well, if I'm dealing with a chemical, not a lollipop recipe, I'm going to use the what? I'm going to use the formula mass, the mass of this. But look what they gave me. They gave it to me already. So that's my bottom number. Please, if they're going to give you the gram formula mass, use it. Okay? If you want to practice doing it on yourself, it will come out to be 84. What's the part they're asking for? That's important. Mass of carbon. Well, there's only what? There's 1 carbon. And we know the mass of 1 carbon is 12 from the periodic table. So 12 over 84 times 100. Okay, I'm assuming everyone knows that if I go to the periodic table, the atomic mass of this 1 carbon, and 1 mole of this, 1 mole of carbon, the atomic mass is 12. That's where I'm getting it. Okay? I showed you how to do that earlier. So that's what you need to do there. So they want you to determine it, not just set it up. So 12 divided by 84 times 100, and I get 14%. I think it's good enough. 14%. All right. Moving on. And last one, I believe. Not hard questions. Please don't look at these part 2s or any of these math questions as something to be intimidated about. I was inspired to do this because I saw so many students getting so intimidated. These are the same types of problems you just have to identify. So determine the concentration expressed as percent by mass. All right, of the salts in the original sample of seawater. All right, well, I can do that. Okay, percent by mass is part over total. Well, what's the part? Well, we must have some salts dissolved in water. Okay, they said the 10 grams of solid salts remained after I boiled it off. Well, boiling is only a physical change, so therefore the 10 grams are what was dissolved, and that's my part. So 10 grams is my part, and what was the mass of the entire solution? Oh, 30-gram sample of the seawater. So 300 grams is my total times 100. You can really see now, people, that this is really hard, or I should say doable. Part over total times 100. I think we all can identify that. All right, so 10 divided by 300, and we times that by 100, and we get 3.3%. Not bad, not bad, right? Okay, well, there is one more problem that I'm going to do in this video, and there's plenty others you can do, and you have the old packet that really relates to this percent by mass. Okay, and it's called part per million for a couple of different reasons. Let's go see how many part per million questions have existed in the last 6. There's only 3, but 3 out of 6 is 50% of the time. And the reason I want to show you this is percent by mass and part per million are definitely related. Not because you're using the formula mass sometimes if it's a chemical, but how it's set up. It's still a part over total type of scenario. Let's go to table T and I will show you. So if we look at percent composition or percent by mass, mass of the part over the mass of the total times 100. You can see that part per million is essentially the same formula. Mass of the solute, which is what's being dissolved, that's the part we're asking for, over the total mass of the solution, that's the total. Okay, instead of timesing it by 100, we times it by 1,000,000. So essentially, it's part over total like this. Instead of timesing by 100, times it by 1,000,000. Okay, so let's go see some problems. Okay, simple question. Which type of concentration is calculated when the grams of the solute is divided by the grams of the solution? The result is multiplied by 1,000,000. It's a part per million. Okay, hope you get something like that. Okay, but January 2013. Here's another kind of question. It's a part 2. It's not quite as clear, except they're giving you part per millions in the table there. Concentration of CO2. Look at our question here, 68. They want to set up for calculating the mass of carbon dioxide in a 100-gram sample of air in 1980. So in 1980, we have a concentration of 338.7 grams. So if we go to table T, our part per million formula is ppm equals the part that we're talking about, mass of the solute, over the mass of the solution, total, times 10 to the 6, fancy way of saying 1,000,000. Now, they want a setup for the mass. Well, what did they give me? Well, they gave me that the concentration at 1980 is 338.7 part per million. So I write it 338 ppm, and they're looking for the mass of the part. That's up here. They told me the total mass of the sample in question 68 was a 100-gram sample down here. Okay, so all we got to do is, what was that sample? My short-term, 100-gram, yeah. My short-term memory is gone at this height. 100-gram sample. And then we're timesing it by our 1,000,000. 6 zeros, make sure you have them if you're going to do it that way. And that's all they wanted, the setup. All they wanted. Of course, you should be able to solve for that number. Algebraically, that 100 would go to the top and the 1,000,000 would go to the bottom to solve for x, because this is over 1 and this is over 1. So you should be able to solve for x if the question asks for it. And of course, our last one, there's only 3 out of 6. They want just a setup for calculating the concentration in parts per million. Okay, so it's part. Okay, how much copper plus 2? Well, we have a total sample of 550. That's my total, just like percent by mass. The part is a small number. You can put that in there. 6.75 times 10 to the negative 4. And it's equal to part per million, which is for very dilute solutions. And we times it by 1,000,000, just from table T. Just a setup. Okay? And of course, you should be able to calculate that as well. This number divided by 550 times 1,000,000 would give you the actual number, but they just wanted the setup. So these questions that I went over in this video represent questions that pop up a lot, okay, probably the most. And I hope you can see from this how they are interrelated, and I hope this helps.